So, we talked about three conditions in transistor operation in common emitter mode, and that are cutoff, active and saturation. Okay. So, cutoff, when the forward bias of emitter base junction is not done. So, no base current, no collector current, that is cutoff, that is simple to understand, simplest to understand. Then we have active region, and active region means the collector base junction is prepared, is ready, is strong enough to draw electrons from this base which are injected by the emitter. It is sufficiently reversed bias. So, if you increase this IB little bit and more electrons are there in the base, the collector is ready to take them also, and hence that ratio IC by IB equal to beta is maintained. So, that is the active region in which IC over IB is beta and it is maintained whatever. And then we have the saturation region. This is slightly tricky to understand, this saturation. This is when the collector is not sufficiently reversed biased, either it is 0 bias or little bit forward maybe. So, that if the electrons are there in the base region, it is not able to attract them well. So, its capability of drawing electrons from this base region is saturated in that case, and that happens when you have large current in this load resistance. Remember this, our figure. You have this load resistance RL, and then you have this biasing VCC. This side you have RB and this VBB. So, suppose I have some reverse bias to start with. Let us say we have put some VCC to start with and it is reversed bias, this current is very small. Suppose this VBE is very small, this current IB is very small, this is IE, this is IB from this side, this is IB, and then this is IC. So, to start with, suppose we have our biasing battery low, so that this IB is low and this is reverse bias, and IB is low, then correspondingly it will be beta times IB, but that is also low. So, that this VCE, what is VCE? VCE is between this point and this point, or this point and this point. This is VCE. So, that VCE is VCC and minus RL times IC. So, suppose we start with a small IB, we start with a small biasing here, and then you have a small IC, and then VCE is good enough, large enough. This quantity is small, it's VCC, and VCC is good. Let us say 2 volts we have put, and if this IC is very small, this will still be reversed bias, and it will collect the electrons, and this condition will be satisfied. But what happens if I increase this? If I increase this VBE, if I increase this IB, what will happen? If IB is increased, IC is increased, and if IC is increased, then VCE is decreased. So, that reverse biased voltage decreases, okay? And if reverse bias voltage decreases, the strength with which it is attracting these electrons decreases, and there could be a situation, if you are increasing IB, there could be a situation that this IC is now so large that this thing is close to 0, and in that case your reverse biasing is gone, although the same battery is there. We have not changed this RL or this battery, the same is there, but by just increasing this, you can get a situation where now IC is increased so much that this drop this drop is now very small, because this drop is VCC minus RL and IC. The current is going in this direction, remember, the current is going in this direction. So now we say that it has reached saturation stage, and if you increase this IB further, since it is no more sufficiently reversed bias, it will not follow this equation, it will not draw that much of current, and it will almost be constant at its maximum value. So it has saturated. The capability of drawing the electrons from this base is saturated, and therefore this current is no more increasing. Even if you are increasing IB, this is not increasing. So that is the saturation region. So these three regions we talked about. Then we talked of the input characteristics, which is very simple IV characteristic, and then the output characteristics, which are very important. So in output characteristics, we have this VCE and we have this IC, and then we saw that the characteristics are of this type. So this is for one IB. This is for one IB. Let us say IB is 10 microamperes. And then if I go for another IB, then this curve goes something like this, like this. This is for IB equal to 20 microampere, and so on. You can go on drawing. And here, this is the active region. Okay, this side is active region, where the VC is so large that this base collector junction is very nicely reverse bias, and it is following that IC by IB equal to constant. So even if you increase or decrease this VCE little bit, the IC remains the same because IB remains the same. So it is decided by IB. The collector current is decided by IB. That is how it should be. It should be in a reverse bias condition. The reverse bias, if that start deciding, that means you are in this saturation zone. So this part is that saturation zone. This part is saturation. This part is saturation, like that, and this flat parts are active. Okay, now based on this, let me start with an application for which the transistor is primarily known, and that is transistor as an amplifier. Right? Amplifiers, you know, I am speaking, although I am trying to speak loudly, but may not be loud enough to let 100 people or 1000 people listen to this voice. So what do? We convert this audio into a voltage signal. So whatever vibrations are happening, some kind of microphone, so that diaphragm vibrates and that creates a voltage signal. And so you have voltage signal, and then you amplify that through that amplifier circuit, and then that amplified voltage signal is fed to bigger speakers, and those diaphragms now vibrate with larger amplitudes. But that variation with time, that kind of waveform that I am generating by speaking, that waveform has to be preserved. Only the amplitudes are to be enlarged. So that variation, the kind of variation, that variation must remain there. So that is how the things are amplified, voltage signals are amplified. So this transistor is the basic unit for amplification, and the basic theory, which we call single stage amplifier, can be very easily understood using this diagram and using this diagram. All I have to do is that with this biasing, I have to add that voltage signal. So voltage signal could be, if you draw this voltage signal as a function of time, then it could be something, it could be some kind of a signal, some kind of an varying signal, time varying signal. And what we wish is that same signal, similar signal is generated after amplification, only these amplitudes are now larger. So, everywhere. So, if you have a, let us say, JPG type of picture, you just stretch it to increase this amplitude, keeping this time axis same. So, you stretch it in y direction and these amplitudes are increased and this scale remains the same. So, that is how we need. So, this signal, this voltage we add here in this biasing. Okay. So, here if I add this, let me draw a fresh diagram also I can draw. So, same diagram I am repeating. So, this is RB and then I have this signal here and then I have this biasing battery. And this side is same. And this signal is supposed to be small, right? This signal is supposed to be small. This biasing voltage is there, and you have chosen this biasing voltage here and here in such a way that you are well in the active region. Okay. So, in this diagram, let us say I am somewhere here. When there is no signal, let us say we are somewhere here. Let us say we are somewhere here. That means when this signal is 0, then this VCC and this VBB have such values. They have such values that the base current is okay. This is the base current. This base current is say 10 microamperes, and this VC is something. This VC is something, maybe let us say 4 volts. So, this VC is 4 volts from here to here. From here to here, this is VCE, which is also your output voltage, right? This is collector, this is collector, this is collector voltage, and this is emitter voltage. This is emitter voltage. So, this VCE is nothing but the voltage between this point and this point, which is also called output voltage. So, this is the scenario, and suppose in this condition this VCE or VO is your 4 volts, right. Now, the signal is there. So, at a certain time the signal is 0, but then as time passes it changes. Let us say it changes by a small amount delta Vs. So, this Vs which was 0, from Vs equal to 0 it goes to Vs equal to delta Vs. What will happen to IB? The IB will also change. Okay, the IB will also change. And if you write equation, what is from this point to this point? This is VBE. So, let me write VBE equal to, okay, VBE equal to. So, I am trying to write VBE, this voltage. What is this voltage? This voltage is, here this is 0. So, this is VBB, here it is VBB. So, it is VBB and then plus Vs, which is delta Vs here, and then how is the current? This is how the current is. So, the voltage is dropping. So, it is minus and IB into RB. Okay. So, this is how it is. VB is this VBB and then plus this delta Vs, or let me write it Vs. Let me write it Vs. Let me write for general time. plus Vs and minus IBRB. This is at the general time, or say at some time t. And then at t plus delta t, what happens? So this delta VE changes. We are interested in changes, remember, changes. So change delta VBE is equal to change in this is 0, VBB is fixed, so change in this is 0, then this delta Vs, and then minus change in IB, and RB is fixed, right. So this signal is changing. At certain time it has some value which let us say Vs, at certain time it is Vs, and then after delta t time it has become Vs plus delta Vs. So this signal has changed. So this is this, and similarly here when the signal is changed, then this biasing voltage has changed, and if biasing voltage has changed, this current will change from 10 microampere to something else. So that is I am writing here delta IB, RB is fixed, VBB is fixed. So delta VBE is this. Now this VBE, you cannot really change it much. Why? Because if you remember, the characteristic is of a PN junction, and in this case base emitter junction, input characteristics, VBE here and IB here. It is like just a PN junction with the values of IB in microampere range, in this case base emitter case. Now this VBE has almost a value. You cannot go beyond that. If you are too less, then you are in the cutoff region. Your current is 0 or almost 0, and then suddenly it rises. So you cannot really change this VE much. So this delta VBE, that means change in VBE because of this signal, is going to be very small. But how can that be? If I am putting a signal here, let us say I am putting a signal of 0.5 volts, and this is let us say 3 volts. So is it not 3.5 volts? How can this VBE remain the same? That is because of this current here. The current changes, this drop changes. VBE almost remains same. Whatever change you bring here, correspondingly the current changes, this drop also changes to keep this VBE almost the same. So, and the same thing you can write from here also. If you write this as 0, if you take this as very small and write as 0, then you have 0 equal to delta Vs minus delta IB and RB. So delta Vs is equal to delta IB into RB. So whatever voltage change in the biasing is brought about by this signal, that is compensated by the voltage drop, increased or decreased voltage drop here. So you have this equation. So your signal can be written like this. The variation in signal in time delta t can be written like this. Now let us look what happens on the output side, on this side. So for this we already have this equation, VCE is VCC and minus RL IC. So if I write delta VCE, and remember VCE is your output voltage, is delta VCC, which is 0, and then minus RL will remain there and delta IC. Okay, VCE is the voltage between collector and emitter. Here is the collector and here is the emitter. So this voltage, and this is same as this voltage, and this is the output voltage. So VO or delta VO, V output, is minus RL times delta IC. If I look at this diagram, this characteristics, output characteristics, what is happening? by changing this biasing voltage, you are changing IB. So, initially if this is the point representing the transistor operation, then it has changed from 10 microampere to something else, say 10.5 microamperes. That means from this you are going to another characteristics. Your transistor operation was represented by this point, now it will be represented by a point on this characteristic, on this, which corresponds to that IB equal to that changed value, say 10.5 microampere or whatever. Okay. What happens to this VCE? That also changes, But then if we are well into this active region, not close to saturation region, even if it changes a little bit, and what will happen? Will it increase or will it decrease? It is minus RL into delta IC. So, it will decrease, but if you are not here, you are somewhere here, doesn't matter, your IC remains the same, because this is flat. In active region this is flat. So, IC has changed from here to here, and the change in IC, that is the delta IC, this is our delta IC. Okay, IC was this much and now IC is this much. So, this is delta IC. So, this is how things will work, and if I divide this delta VO by this delta Vs, what I will get? I will get voltage gain. So, if the signal varies by this delta Vs, this output voltage varies by this delta V naught, right. And the kind of variation, if it is all linear, and it is linear, what is that? Delta V naught VO divided by delta Vs, this is minus RL delta IC and then divided by RB and delta IB, and this is beta. We are in the active region, so this is beta. So, this is minus beta times RL by RB, and this is constant. So, whatever is delta Vs, a proportionate change will come in this output voltage. So, the waveform, shape of the waveform will remain same, only the proportionately it will be increased, the amplitudes will be increased, right. So, that is how the amplification has taken place. This signal has been amplified here, right. We are only interested in the changes. Remember, you can always put capacitors and all those things to filter out any DC there, and the time varying part is only taken. One important part is this minus sign here. So, what does this minus sign tell you? It tells me that amplification is there, magnitude it is increasing, because this beta can be 100, 200, etc., and then this is a fixed ratio. But minus tells you that if the signal voltage increases, then the output voltage decreases, and if the signal voltage decreases, then the output voltage is increased. So, if you have this kind of signal here, after amplification what will happen? This magnitude is increased, let us consider only this part. So, this magnitude is increased, but at the same time it has gone down. So, it is going like this, then when it is going down, it is going up. So, it is going up and it is going further down, and then it is going further up, and so on and so on. So, this kind of inversion will take place, everywhere. Okay. So, this is your output voltage as a function of time. I have drawn only a small part, I cannot draw so nicely the entire thing. So, it is this. So, if I draw a better figure, a simpler figure rather, if my signal is like this, then the output will be like this. this will be output and this will be Vs, right. Of course, not a very good drawing, but you understand what I am trying to say. So, the important lesson is that if you use transistor, single stage transistor in this common emitter mode, the amplification is there, but then there is a pi phase change, okay, phase change of pi. During this amplification, phase change of pi takes place. So, this is the basic physics of amplification by transistors, and after that you can make varieties of circuits and put more stages and put different elements and do a better job as required by the problem in hand, but this is the basic physics of amplifier.